The underlying disease process that causes coronary heart disease is atherosclerosis. Atherosclerosis starts in childhood and then becomes chronic and progressive over a lifetime, depending on the burden of so-called risk factors. Among the most important of these risk factors are circulating plasma lipoproteins. Pro-atherogenic particles include low-density lipoprotein, intermediate-density lipoprotein, very low-density lipoprotein, and lipoprotein A. Such particles characteristically contain apolipoprotein B or Apo B. Anti-atherogenic particles, such as high-density lipoprotein, contain apolipoprotein A1 or Apo A-I and other protective proteins. HDL promotes cholesterol efflux from atherosclerotic plaques by mediating reverse cholesterol transport. It is also believed to have a number of protective effects on the arterial wall. The HDL fraction in human plasma is heterogeneous and may be classified into a number of subclasses. Lipid-poor Apo A-I efficiently accepts cholesterol and phospholipids effluxed from cell membranes by the ABCA1 transporter and forms nascent discoidal HDL, also known as pre-beta HDL. Nascent HDL particles are preferred substrates for lecithin cholesterol acyltransferase, or LCAT, which esterifies the cholesterol associated with them. Cholesterol esters accumulate in the particle core, giving rise to spherical HDL3 particles. Larger spherical HDL particles can accept additional cholesterol from ABCG1 and SRB1 receptors on cell membranes. Through continuing lipid accumulation within particle cores and remodeling by various plasma factors, small HDL3 are converted to larger HDL2 particles. Ultimately, cholesterol stored in large, mature HDL2 particles is efficiently taken up by hepatic receptors and further metabolized by the liver. The various HDL subclasses thus have unique biological activities that contribute to the overall function of reverse cholesterol transport. An abnormal distribution of HDL subclasses may result in impaired reverse cholesterol transport and accelerated atherosclerosis. Therapeutic interventions which specifically raise HDL cholesterol levels are being investigated for their potential to address the cardiovascular risk that persists in patients whose LDL cholesterol has been lowered with statin therapy. Among the targets being investigated for such interventions is cholesterol ester transfer protein, or CETP.
The production of endogenous cholesterol is a complex and energy-consuming process. CETP in fact redistributes cholesterol among the different plasma lipoprotein fractions. But given modern lifestyles and high cholesterol diets, its activity in humans contributes to increased LDL cholesterol and decreased HDL cholesterol levels, potentially aggravating atherosclerosis and raising cardiovascular risk. CETP is a glycoprotein. It is synthesized mainly in the liver but also in adipose tissue, and it's attached to lipoproteins. CETP transfers lipids from one lipoprotein particle to another in a process that results in the equilibration of cholesterol esters and triglycerides between different lipoprotein fractions. The overall effect of CETP activity, therefore, is a net mass transfer of cholesterol esters from HDLs to triglyceride-rich lipoproteins and LDLs, and of triglycerides from these triglyceride-rich lipoproteins to HDLs as well as to LDLs. In sum, CETP promotes the transfer of cholesterol esters away from anti-atherogenic HDLs to pro-atherogenic Apo B-containing lipoproteins. These functions of CETP can be considered pro-atherogenic, and they suggest that reducing CETP activity could potentially reduce atherosclerosis. A deficiency of CETP activity has been associated with increased HDL cholesterol and decreased LDL cholesterol levels, a profile that is typically anti-atherogenic. In addition, CETP is known to transfer cholesterol between HDL subfractions and assist in remodeling, a function that again potentially could be anti-atherogenic.
The The structure of CETP, elucidated by crystallographic studies, reveals a boomerang-shaped molecule divided into 4 structural units. These include a central beta sheet flanked by N and C-terminal barrels, as well as a mobile C-terminal extension designated Helix X. A central tunnel of 60 angstroms runs lengthwise through this structure, providing a hydrophobic environment to contain 2 molecules of cholesteryl ester or triglyceride. It is accessible from 2 openings on the protein's concave surface. It has been hypothesized that when CETP binds to a lipoprotein particle, Helix X inserts itself into the particle's surface and governs the access of neutral lipids into the N opening of the tunnel. Another flexible structure, the omega-1 flap, may serve as a lid for the C opening. When the tunnel is filled, its openings are plugged by an amphiphilic phospholipid molecule at each end. The concave surface of CETP complements a sphere 10 nanometers in diameter, which is the approximate size of a nascent discoidal HDL particle. However, the ability of the N and C terminal barrels to twist around the central beta sheet endow CETP with conformational flexibility. Thus, the curvature of CETP can be adjusted to complement the radii of many different sizes of lipoprotein particles. This conformational flexibility of CETP is crucial to its ability to bind to lipoprotein particles of a wide range of sizes, in order to shuttle cholesterol esters and triglycerides between them.
Preclinical studies with mice and rabbits have shown some very interesting results where atherosclerosis is concerned. It has been known for a very long time that it's very hard to induce atherosclerosis in mice, while it's very easy to induce atherosclerosis in rabbits. We did not know why this occurred, but we now understand that mice naturally do not have CETP and rabbits naturally have very high CETP activity. So that led us to believe that CETP activity in these animals is driving atherosclerosis. In addition, we have used drugs or antibodies to lower CETP activity in the rabbits, and that protected the rabbit against the development of atherosclerosis. So all these data combined make it highly likely that inhibition of CETP in humans might also slow down atherosclerosis and prevent heart attacks. Studies in human subjects have revealed that mutations in the gene coding for CETP are not rare in Japan. And quite a large number of these subjects were enrolled in a study called the Honolulu Heart Program. When you study human individuals with mutations in the CETP gene, you notice that their CETP activity is down and their HDL cholesterol is up. And if it's considerably up, like above 60 mg per deciliter, in fact, the net effect of that is a protection against coronary disease. So also the data in humans confirm what we have seen in the rabbits, namely that low CETP activity is associated with protection against atherosclerosis.
Recent studies have shown that besides affecting the net transfer of cholesterol esters from HDL to pro-atherogenic lipoproteins, CETP facilitates the transfer of cholesterol esters between HDL particles. This may be instrumental in generating a polydisperse HDL population, necessary for the functions of this lipoprotein class. There is evidence of a direct role for CETP in conversion between different HDL subclasses. When HDL3 particles are incubated in the presence of CETP, the appearance of smaller pre-beta HDL particles as well as larger HDL2 particles is observed. This change in size was abolished by antibodies which inhibit CETP activity, implying that HDL conversion is mediated by CETP. Smaller subclasses such as pre-beta HDL particles are acceptors of cholesterol effluxed from macrophages via the ABCA1 transporter. Thus, although other plasma components such as LCAT contribute to HDL remodeling, it is conceivable that eliminating the beneficial role played by CETP in pre-beta HDL generation might compromise the first step of reverse cholesterol transport. This implication must be considered carefully when devising therapeutic interventions that target CETP as a means of raising HDL cholesterol. The following module will discuss various therapeutic approaches being explored for their potential to raise HDL cholesterol by the inhibition or modulation of CETP activity.